All right, our next speaker this morning is Isabella Zadoyan, who has joined us this summer from Cal Poly San Luis Obispo. She's been working this summer with Nicole, and she'll tell us about their project together, comparing galaxy metallicity gradients from cosmological simulations and observations.
Awesome. Thank you for the introduction, Gwen. So hi, everybody. I'm really excited to get to tell you all what I worked on this summer with my mentor, Nicole, to better understand how I was comparing galaxy metallicity gradients from simulations to observations. We need to look at the M-sigma relationship. So the M-sigma relationship is the relationship between a galaxy's supermassive black hole mass and the velocity dispersion of the stars within the galaxy's bulge. Here is a plot of the M-sigma relationship from Tremaine et al. 2002, where they measured the stellar kinematics, gas kinematics, and maser kinematics to determine the black hole mass, which you see on the vertical axis, over the different velocity dispersions. What's really important about this is that it shows there is a strong relationship between black holes and their galaxies, and that these two things actually evolve together, which is something that we don't fully understand yet, and something that I'm working to better understand with this project. Further motivation for my project comes from work from my mentor. She found that galaxies above and below the M-sigma relationship have different metal enrichments. So galaxies that have a more massive supermassive black hole than the M-sigma line predicts actually have a lower metallicity in the center of their galaxy compared to galaxies that have a lower supermassive black hole than predicted by the M-sigma relation. So as an overview of what I'm going to be talking about today, I'm going to move on to introduce the Romulus 25 simulations that I use to analyze different galaxy properties, as well as talk about the observed galaxies that I used to compare to the simulations. Moving on from that, I'll talk about our two results, the first being from comparing observations to simulations, and the second being from comparing simulated galaxies above and below that M-sigma relation line. So here's a plot I made of the M-sigma relation with the mass of the galaxy's supermassive black hole on the vertical axis and the velocity dispersion on the horizontal axis. The pink line is the M-sigma relation line from Cormandy and Ho 2013, and all the gray circles are the simulated galaxies from the Romulus 25 simulation that are my sample size for this project. So what is the Romulus 25 simulation? The Romulus 25 simulation is a large-scale cosmological simulation that advances dark matter and gas from the beginning of time to our present-day universe. This simulation outputs about 1,000 galaxies, ranging from massive galaxies and dwarf galaxies that I can then select and analyze different properties of. Some of the properties I can look at are the gas density, gas temperature, the stellar map, and the gas velocity, just to name a few. What we can get from this is a picture of the simulation halo number 43. And what we can see is that the gas is most dense in the center, as well as is cold in the center of the galaxy. We can also visualize where all the stars are in the galaxy, and we could see the gas movement within this galaxy. Now, talking about the observational galaxies that I used to compare, the three galaxies we used are M31, the Andromeda Galaxy, M81, and M106. We chose these galaxies because they are well-studied galaxies, and we compared these galaxies to simulated galaxy analogs, which I'll talk a little bit more about later, in order to kind of determine why, compare the observations to simulations. So these simulated galaxy analogs were chosen because they have similar black hole mass, stellar mass, halo mass, and velocity dispersion to our observed galaxies. Here's a picture from NASA of each of our observed galaxies that kind of give us a better idea of what these galaxies actually look like. And then going back to our analog criteria, so these are the simulated galaxies that we chose to be similar to our observed galaxies. These galaxies have a similar black hole mass, stellar mass, halo mass, and velocity dispersion to our observed galaxies. In addition to this, we also looked at the star formation histories of these simulated galaxies to get a better understanding of what they've been doing in the past, and to also make sure they were still star forming at present day when we're actually looking at them with the simulation. So here's a plot I made of the M-sigma relation from before. I just added our observed galaxies, and here are actually the simulated galaxy analogs to these galaxies. Moving off of that, here's a picture of all their stellar maps of the simulated galaxy analogs and their observed galaxies. This is more so to just kind of get an idea of what these simulations look like, to get more of a physical picture. And what you can see is that some of our analogs actually do look sort of similar to the observed galaxies themselves. The simulation actually tells us the metal content within each galaxy. So here's a plot of the metallicity of Halo 60 over the galaxy's radius. And right here we could see that it has the highest metallicity in the center of the galaxy. Observers, on the other hand, measure oxygen and hydrogen abundances to determine the metallicity of galaxies. So in order for us to compare our simulations to how observers measure the metallicity, we need to look at the hydrogen and oxygen abundances. So although the simulation gives us the metal content within each galaxy, we look at the oxygen abundance and the hydrogen abundance in order to determine our mock metallicity, which is the metallicity in oxygen and hydrogen abundance in this log OH plus 12 quantity. That's similar to how observers measure it. So what we see from this measurement of Halo 60's oxygen and hydrogen abundances to get the metallicity is that it's a relatively flat profile, which I'll discuss more later. So when we're comparing our metallicity from observations to simulations, I put them all in the same plot. So here are the simulated galaxy analogs of galaxies from the simulation that are most similar to our observations. And this is for M31, the Andromeda Galaxy. When we populate this plot with observed data from H2 regions and from planetary nebula, we see that our simulated galaxies have a higher and flatter metal profile than observations. This was also consistent with the two other observed galaxies and their simulated analogs that we were using. So now switching a little bit onto the motivation from my mentor, where galaxies above the M sigma line have lower metal in the center compared to galaxies below the M sigma line, we wanted to better understand where this could possibly come from. So I selected galaxies above and below the M sigma line. These are simulated galaxies, and I chose them in vertical pairs to have similar velocity dispersions, but also to have similar stellar mass and halo mass. The main differences between these compared galaxies is their black hole masses that are above and below the relation. Looking at these simulated galaxies, we can look at certain properties, for example, their gas density. So when we look at their gas density across the M sigma line, we see there's no clear trend between these galaxies, which is okay because that's not really what we're focusing on. But this is just one of the ways that we wanted to kind of visualize what all these simulated galaxies look like. Another way we wanted to look at these comparison galaxies is through their star formation histories. In red, you have the galaxy with an overmassive supermassive black hole, and in blue is the galaxies with the undermassive supermassive black hole. And what we can see from this is we wanted the galaxies to have similar star formation histories. The plot on the right is an especially good image of this, and we also wanted to have these galaxies have similar star forming rates at present day, which is highlighted in yellow. So when we look at the oxygen and hydrogen abundances to determine the metallicity of the gas within these simulated galaxies, we see still these flat metallicity profiles, even though we're looking now at the galaxies with overmassive black holes and the galaxies with undermassive black holes. This was not what we expected to see from the motivation from my mentor. This was also what we saw when we were looking at more of our galaxies above and below the M sigma line. There was no clear trend between the galaxies that were overmassive and undermassive in their black holes. So this caused us to actually kind of pivot, and we decided to look instead at the stellar metallicities. So when we look at the stellar metallicities, now we're looking at the iron and hydrogen abundances within the galaxies. And what we did find was the observed predicted trend from my mentor. We found that galaxies in red with a more overmassive supermassive black hole have a lower metallicity in the center of the galaxy. We also found this when we looked at more comparison galaxies above and below the relation. So now going back and comparing these stellar metallicities to observations of stellar metallicities, we found that our simulations are still higher than predicted by observations. So moving off of this, we still want to compare more stellar metallicity comparisons, as well as compare more stellar metallicities observations to simulations. And we want to work to figure out why our simulation metallicities are consistently higher than observed metallicities. So in summary, I compared measurements from the Romulus 25 simulation to observers' metallicity data, and we found an unexpected flat gas profile that also did not trend with what was predicted from my mentor. But we did find that when we look at the stellar metallicities, we do see the expected trend, but our metallicity values are still higher than simulations. So moving forward, we still want to look at more comparisons to confirm or reject my mentor's theory. Thank you.
Hi, thank you. It was very interesting. I was wondering, so to compute the metallicity in your simulated galaxies, did you use the hydrogen and oxygen abundances of all the gas particles within a simulation?
So when we're looking at the gas particles, we selected the cold gas particles. So we had a temperature cutoff and then used those particles to calculate the oxygen and hydrogen abundances.
And what cutoff did you use?
I believe it was 2 × 10⁸ 9th. I don't remember entirely, but yeah.
Thank you.
Can you explain why the mass of the supermassive black hole would control the shape and normalization of the metallicity profiles?
Yeah.
What's the physics behind that?
So the theory as to why we see this relationship with galaxies with a more overmassive black hole having less metallicity in the center is because the more massive supermassive black hole is actually expelling the metals from the center of the galaxy to the edges of the galaxy, which is why we see less in the center.
Yeah, great talk. I was curious as to, is there a particular, or do you have any predictions as to why the expected trend in terms of metallicity was visible in stellar populations, but not in cold gas?
Yeah, that's a great question. Give me 1 second. So this is kind of just an extra informative slide I have. So when we're looking at the gas, we're looking at present day, and we're looking at young stars that are glowing the gas around it. So that's why we're measuring the oxygen and hydrogen abundances. But when we look at the stellar populations, we're looking at the full galaxy's history. So that's kind of why they show different trends and why we see the predicted trend for my mentor in the stellar, but not in the gas.
Okay, thank you.
Let's think of